It's interesting. When Dave first reached out, he suggested I speak about ethical AI. And I was delighted to do so, but then I was like, that's not a great opening keynote. I think it's a super important topic, but it feels strange to set the theme for a 3-day conference on machine learning by focusing on some of the areas where potentially machine learning could go wrong, or some of the areas where we need to think about fixing things. I'll mention that in my talk, but instead what I wanted to do was just set the tone for you over the next 3 days in providing an invitation to think about current developments in machine learning through a particular conceptual frame. So we'll start off with images that are presumably familiar to everybody in the audience. If we note, we start off with 1956 Arthur Samuel's checkers playing system on the IBM 701 system. 1997 Gary Kasparov playing the famous chess match against Deep Blue. 2016 Lee Sedol beating losing to AlphaGo in the Go championship, and then 2009 the Dota 2 OpenAI video game achievement. So if we look at these systems and we think about them as representing the imagistic history of artificial intelligence, it's mostly a bunch of dudes with boards in front of them, right? There's this duck, duck, goose odd thing in the corner that is the contemporary manifestation of OpenAI, but largely this is humans playing games. And this is how we think about what this technology could mean for humanity. And this is not a coincidence. So John McCarthy, one of the founders in the field, and Egg Feigenbaum, in their 1990 obituary to Arthur Samuel, the checkers player in the corner, said that video games are what fruit flies are to genetics. Fruit flies are cheap and easy to keep, and games are a good measuring stick for us to communicate the achievements that we've made with applied mathematical models in computer science. Probably because, to capture the public imagination, having images of vector spaces or functions in multi-dimensions, in particular with our measly human cognition system that can barely conceive of 4, it wouldn't have the same level of excitement and press attention that it gets. But let's focus on this goose in the Duck, Duck, Goose. Right, so there's something really interesting in the way in which OpenAI advertised its win in Dota. On the one hand, we have the human means of cognizing phenomena. Kant, the 18th century philosopher, said that time and space aren't quite what we think they are. They're the form of our perception. We just so happen to view the world that way because so our brains are constructed in these physical bodies where we as agents interact with our environment. And the AI view, if you will, is to cognize phenomena in the forms of probabilities and statistics. Slightly different. So while most of the time we think about progress in AI as continually being able to replicate more and more human capabilities, what I'd like to invite us to do today is say, what would happen to our narrative if instead we took this Dota 2 view of progress in machine learning and considered this dialectic, if you will, as a back and forth between human and machine ways of representing phenomena in the world? What would our history look like, and where would we be? So I'll talk about 3 ways to interpret this question. The first is a very cursory overview of the impact that machine learning is having in the world of enterprise applications. And I think we can summarize it as we're taking off the rules-based straitjacket. So there's a quotation from Jeff Bezos from 2016 letter to shareholders where he says, basically, in the past 20 years, we've used systems to automate tasks which programmers could describe with clear rules and algorithms. If this happens, then that happens. Binary expressions, Boolean logic, etc. To make that happen, however, there's tons of complex things that occur in the world that we try to automate, but we have to reduce them down to a simplified expression that doesn't take thousands and thousands of jobs and commands to execute some program. But what's happening with machine learning is that we're shifting from having to stick with programs for which we can write clear rules and algorithms to loosening this constraint to tasks where those rules are harder to describe. So going back to this example of the game of Go, the 11th century Chinese philosopher Shen Kuo in the dream pool essays, made an estimate of the number of moves that there are in a game of Go and counted at about 10 to the 172, which is more than the number of grains of sand on the Earth or stars in the observable universe. So if we think about that, if we were to write out every single possible constellation and permutation of moves, it'd be a lot of lines of code, right? It'd take a long time to run, so long that it's just not feasible. So if we shift that paradigm and instead import a bunch of training examples, going to AlphaGo 0, just turn it into a pure optimization system, suddenly we can make some traction with tasks that we couldn't use using methods that relied upon humans simplifying down the problem to get to a point where they could program it automatically. But of course, if we don't write out the rules, we need data. And back in Fast Forward Labs, where I worked at a couple of jobs back, we used to talk about basically this Maslow's hierarchy of data science capabilities, where you start off with what we used to call big data, our ability to process, collect, and store data at scales that were formerly too prohibitively expensive to do. Once we have a lot of data, we can do analytics, so we can count things, we can add, subtract, multiply, and divide, so that we can get insights into what happened retrospectively to inform better future decisions prospectively. Move into data science, where we can go from these sort of elementary operations to building out functions in the form of mx plus y equals mx plus b. Maybe changing the slope of our curve as we get new data points to fit our models to make predictions about the future. Get into machine learning, we'll start to add in a feedback loop where we don't just import in models making probabilistic guesses about what might happen, but those models are changing over time as we get new data. And as we go into deep learning, going back to this human versus machine, we shift from having our scientists work through features and handcraft features through engineering with associated weights to filled out functions, to having the machine just throw in a bunch of data and learn those parameters itself. And then back to AI, in our definition earlier on, whatever computers can't do until they can. So a sliding scale of capabilities depending on where we stand in the psychological spectrum of historical development. So in terms of what this means for applications, I'll go through a couple of sectors. So in marketing, back in the early days of data and analytics-based marketing, we'd focus on events. And it would be something like, if you're a bank customer and you reach 30 days after acquiring a new credit card, send out some email to get the customer to take a new action. In a machine learning-oriented, probability-based world, we don't have to have every customer get the same email on day 30. We can say, well, let's look at Kathryn. Based upon her actions, based upon what we've seen, it looks like she's got an 82% likelihood of possibly being interested in this rewards offer. So we're going to send her one, but we're not going to send one to her friend Joe, who, based upon his actions, only has a 62% probability. So we're going to set a threshold, and based on the outputs of our models, differentially treat clients to lead to some optimal business return. In the world of security, in the rules-based world, in the heyday of companies like Symantec and McAfee, when we had a malware detection system, we needed to start with a sacrificial lamb, so an organization that had been hacked. The systems would find that code, brand it, understand what the spectrum was, and then update its databases so that other Symantec customers were now immune to that particular piece of malware. So in the machine learning version of the same problem, as opposed to having to wait to find the exact expression from the malware, we can find something that looks just about like it and quarantine off potentially malicious code before it actually infects an organization. This company, Cylance, was founded, I think, in 2012 or 13, subsequently acquired by BlackBerry. So they've done pretty well for themselves. And then third, this is sort of an evolution of different kinds of data-oriented techniques for recommendations. So Gen 1, collaborative filtering, we all know this from Amazon. If you come in and you buy a Dualit food processor and a Kenwood K-Max manual espresso machine, et cetera, and I come in and I buy those same two items, the next item recommended to me is going to be based upon the next item that you've bought, right? So we're going to set up this matrix, and we're going to make correlations between your activities and my activities. The problem with this, as we know, is the infamous cold start problem, where if you don't have a lot of data on me, you're never going to know where exactly I fit into a matrix to correlate my actions with somebody else's. So with the rise of machine learning techniques that can work with richer data, like images and text, we can come in and shift around the structure of our recommenders so that I might go in and say that I'm looking for a nice camel coat, and the image classification system has enough ingenuity to parse out the semantic distinction between my looking for a coat and my looking for pictures of handsome African-American men, right, to try to suggest objects and images that might be interesting to me. Now, to sum up this particular section, this is great, right? So we've broadened the range of applications that we might, and tasks that we might automate, because we're not constrained to these rules. But we make a big Mephistophelian deal in working with these trade-offs, because the output of these algorithms are not exact. They're, to use the language of Leslie Valiant, probably approximately correct. And that's all fine and good when you're building a product recommender for a company like Amazon. Make a mistake, worst comes to worst, you have sort of a clunky recommendation for a customer. But it can be daunting for traditionally regulated industries, like auditing firms, who are in the business of providing, auditing firms are not regulated, but auditing firms are in the business of providing certainty to their clients. So if RBC contracts Deloitte or KPMG to do an audit of their financial statements, they're not looking for answers that are just about right. They're looking for a guarantee that their financial statements meet particular auditing criteria. And so as applied machine learning practitioners and product developers, it's really tricky and important for us to find the threshold of acceptable error for an application to even get anywhere. The number of times I've seen prototypes fall flat and not make it to production because an end user is just not comfortable with a potential 10% of their answers being incorrect is astounding. Okay, so to sum up that first category, it was basically around the way in which we as humans would come in and simplify a problem to make it tangible and expressible for defining a computer program versus the way in which we can relax those constraints and, as Andrej Karpathy puts it, allow the program to navigate the search space to find the optimal expression based upon the data. This is opening and broadening the range of applications available from ML. Next topic, how we humans engage with structured expressions of data that might give us intelligence into how our business is doing. So back in 2010, a group of researchers at Northwestern, led by Christian Hammond, built an application called StatsMonkey. And StatsMonkey was one of the earlier natural language generation applications. And what they did was they said, let's see if we can automate baseball score reporting. So if we go and look at our newspaper, we're going to the sports page, it's kind of formulaic what shows up there, right? It's what was the score at inning 2, probability of we have stats on the individual baseball player's particular batting average, and we're basically just going to take inning per inning the score, report it, and give our baseball outcome. So they looked at this and they said, there's not a ton of variations, so I bet you we can write these articles using a machine. They started down this path, and if you were to go back to the news from 2015, you would see a slew of articles talking about the fact that robots were going to replace journalists in writing news content, largely around the kind of news that didn't require a lot of interpretation, but news like company earnings reports, baseball reports, micro-targeted weather reports, where based on my mood, there's clouds above me and there might be sun above somebody else, so we didn't all get the same result. Maybe even pushing this into marketing content automation so that we'd have slightly different language depending on somebody's personality. And then suddenly, come 2016, the advertising for these companies all changed. So we saw less journal articles about robo-journalists and more about automation of business intelligence. So these companies realized that their first application weren't necessarily the killer apps that were going to be sort of the market-making power for this technology, but it was more around automated business intelligence, where the impact is we have so many people in a company who are comfortable working with Excel spreadsheets or going further, writing SQL queries to extract some sort of insight from data in a company. And most people are comfortable with either visualizations, histograms, bar charts, et cetera, or comfortable with words, right? And are looking for an interpretation of the data that is relative to their position. So head of sales might be interested in trends over the quarter. Somebody who's the salesperson for a particular region is interested in that region, et cetera. So you suddenly saw that all of these natural language generation capabilities were shifting from automated journalism to more friendly and interpretable business intelligence. It's a different kind of capability than we normally think about with natural language processing, where we're not going from the mess of human unstructured content down to something that can be cognizable by a machine, but we're going from our structured data to a linguistic interpretation of that data. You'll see things like this product, Wordsmith, created by Automated Insights, a competitor to Christian Hammond's company, Narrative Science, where basically you can go into a Excel spreadsheet now, highlight a row, and have it automatically pop up with a linguistic description of that capability. So this is a one-sided conversation of a dialogue with a database, where we take our structured representation of data and represent it in something that's easier for a human to understand. But what's happening now is that we're expanding this, flipping this around, where the human can ask a question to a database, it can go through, do some operation, and then output a response in natural language. So normally in a company, to go through this process, we'd hand over a question phrased in human language to a SQL analyst who would go through, understand the database, output something that looks like this, right, query through the fields, et cetera, and then take the time to either put that into a Tableau-like representation or something that makes sense to the business stakeholder asking a question. So at Borealis, where I work, we're working on a product called Alan, in homage to Alan Turing, that automates that entire flow. So human comes in, asks a question, SQL analysis conducted. We have to figure out how to classify the output. Should it be represented in natural language or represented in some sort of visual? And then we provide an explanation as to what our response is and how we went about finding it. Where we think this is exciting is that it is opening up opportunities to go into the long tail of questions that can be shown through an analytics dashboard. So if we're going to use something like Tableau, basically a human has to decide in advance, potentially based upon market research of the frequency with which a query might be posed, what they're going to show on their product. And we have sort of fixed templated analytics that show the same thing every time with just variation based upon input in the fields. With a product like Alan, suddenly many, many, many more questions can be asked because we don't have to pre-code something in advance, opening up the user's curiosity. We're not going to answer everything. There might be some that require super complex join operations that are just beyond the capability of the system, but that's cool. So moral of the story, these capabilities make data analytics faster and more accessible, but I think more importantly, they open and unlock human curiosity to have faster interrogation of data sets. All right, final category. So we've talked about easier automation. We've talked about this whole new world of business intelligence that might shift some of the workforce required to make sense of data in organizations. And the last category I want to look at is the inverse, where the application of algorithms to traditionally extremely human behavior and values is leading us to ask new questions around traditionally fuzzy phenomena. So there's a system that my fiancé is building. He's at University of Toronto, called Figaro Analytics, that is a speech and emotion analytics tool to help people like myself be better speakers. So you're watching me right now. You're listening to my words. If you were to use some sort of algorithm, you might be able to classify the sentiment of the content that I'm saying. But there's a lot more emotion coming out of me. I'm communicating more than just what I'm saying. So my facial muscles are moving, eyes are moving up, my lips are turning in different ways, cheeks are moving in certain ways. My voice is modulating either high or low. I'm not somebody who's particular on vocal fry, but were I to be, you'd hear that. So this is a tool that is applying a sequence of classifiers to various signals. Imagine it like signal processing for human beings that we emit as agents in the world and that you're all processing to try to make sense of what I'm saying. And if you were to get a coach to come in and help you be a better speaker, they'd normally give you kind of crappy, fuzzy indications around where you might be able to say something better, might have less disfluencies, but they wouldn't really quantify a description of how you act as a human being as if you were a machine, counting the frequency of your words, using analytics on your voice, using analytics on your face to calculate not the emotions that I'm feeling, but the emotions you suspect my content is communicating to you when I speak. The tool is going so far as to add a quantitative expression of gesture. So if we look here, we have our speaker. We're making a proxy for what openness or closure, what dominance or submission could look like by measuring the angles of one's chest down to their hands. And if you look in the right-hand corner, we can tweak the parameters of which particular feature we want to focus on, if we want to be like the hands person or the shoulders person, to try to give an estimate of how open or closed we are. So I bring this up as an example to say, this is not that the machines are starting to be more human, that the machines are having emotional intelligence. This is that in our efforts to apply an algorithm to a traditionally human domain of activity, we're lending ourselves a more precise and analytic language to potentially improve our own understanding of how we communicate, right? To make sense of something that's always been sort of intangible, like a je ne sais quoi. And this is happening not only in potentially non-consequential areas like public speaking, but also in aspects of society on which our values reside, things that really matter. So I'll give an example with fairness. We think we know what fairness means. So take two kids eating Oreos. We might say, well, it's fair if both kids get 2 Oreos. But then you might say, no, but one of them's 10 and one of them's 3. So fairness is proportional to the size of the kid. So the 3-year-old should get 3 Oreos, and the 10-year-old should get 5 Oreos, and that's fair. So as we attempt to codify these fuzzy values into algorithms, we're forced to ask these questions. And right now, if we take stock, there are 20 different technical definitions of fairness that have been active in the community since 2012. A study done in a paper that came out late 2018, maybe 2019, on the different types of fairness. Sometimes we think fairness is about a group. So if we have a group, one's a minority and one's a majority, we want to make sure that they each have equal outcomes for some, let's say, application to a college or granting of a loan. Sometimes it's an individual. So Rich Zemmel at the University of Toronto has fallen into the school called fairness through awareness, where we say we need to treat similar individuals similarly. So we have input data, we have output of a classifier. If Kathryn is like Joe, Kathryn and Joe should have kind of similar outcomes in the various spaces that our algorithms are working on. So it's not only that we're forced to grapple with the definition of fairness across multiple categories, but the choices that we make have impacts on either the outcomes of the use of an algorithm based on profitability or fairness across the population. So here's an example from a 2016 paper by Morris Hart and co-authors that shows how the choices of our definition of fairness impact the distribution of loans across a population. I won't go through all of the different numbers, but what we're seeing is that we can optimize for profit, which is the blue bars in the bar chart, where basically we shift our threshold for who gets a loan based upon their likelihood to default, proportionate to the number of defaulters in a population. Note that Asian people get many, many more loans than black people in that constellation. Or, flipping it, we can focus on demographic parity, where we provide the same number of loans independent of the ethnic diversity in a population, but with the trade-off that if we're going to provide a lot more loans to black people in this particular example, we're going to actually be providing loans to people who would have a higher likelihood of default. So we're not actually meeting the aims of the organization to optimize for a risk trade-off on minimizing defaulters and maximizing profitability. On the right-hand side, depending on which measure we pick, you see that the profitability curves for the organization really do change. This is tough for organizations. They say they want to be fair, but trust me, they also want to make profits. And these are the hard conversations that you, as scientists, need to be having with executive management as you're applying algorithms on socially sensitive use cases. So, conclusion of this particular chapter is that these algorithms force us to be explicit about human behaviors and values in a way that we haven't necessarily historically had to be. And no matter what the future holds, that's progress. Thanks so much and have a great conference.